Alright, so now we're going to talk about triglycerides. So we're going to keep going through lipids here. And so fatty acids are generally not moving around by themselves. They're usually packaged into triglycerides, or they're used to be used in phospholipids or steroids. The phospholipids are kind of like a modified triglyceride, and steroids are a whole other thing altogether. We'll talk about it when we get there. So triglycerides are typically how you're going to see fatty acids stored in biological systems. They're not floating around necessarily. If you've ever wondered about, so one thing I get asked about a lot, I guess I should put it like that, is when we talk about saturation levels, that tells us melting point. But people always ask about the smoke point of cooking oils as well. And so in general, the more free fatty acids there are, the more fatty acids that are not in triglyceride form in an oil or a fat, because those are triglycerides. The lower the smoke point is going to be, the easier it is to start burning the oil. So if you're wondering about that, now you know. Alright, so what are triglycerides? Well, they are formed from 3 fatty acids. So fatty acids do have that carboxyl group. They are a little bit reactive. We don't necessarily want that floating around, so we're going to take 3 of them. We're going to package them in to a triglyceride, and they are going to be bound to a glycerol backbone. And so this is long-term energy storage. This is like your savings account. So I often talk about carbohydrates being like your checking account or your debit card. This is like your savings account. Like, this is emergency use only. This is long term. So there's a lot of energy density here, but it's very slow to access. And we'll talk about that more later. We'll really talk about that more when we start building towards respiration at the end. But just keep in mind that it's long-term energy storage. So there are multiple biomolecule groups that have energy storage associated with them, but this is like the long-term one. So when, if you're trying to, burn some fat, it's going to take a longer time than if you want to burn through your glycogen stores, if you want to burn through the carbohydrates that you're storing energy in. So those are there to be used immediately. This is here to make sure we've got energy to keep cellular processes running long term. So this isn't going to be, knocked out by just going for a run. It's going to be knocked out over long term caloric intake, monitoring. And you can't lose 10 pounds of fat in a week. I mean, maybe you can, but it's not a healthy way to do it. Like, it is supposed to be burned down slowly. That's how it's designed. So it's to help, get through a week of not finding something to eat, that sort of deal. Not running for 45 minutes. That's a different energy setup. Or going for, if you sprint, that's something else entirely altogether. Then you go anaerobic. So we'll get into all that later. So what does this look like? Let's just get right into it. So I'm going to draw a very, very, very simple triglyceride. So it's going to have 3 matching fatty acids. That doesn't have to be the case. That doesn't have to be true at all. They can be 3 different fatty acids. And I'm going to draw a saturated one, so I don't have to draw any double bonds in it. So I won't draw, but they could be unsaturated. And I'll talk about that a little bit as well later in the video. So we are going to have a fatty acid chain. Okay, but our carboxyl group is not an OH anymore. It's going to go to a glycerol backbone. So it's not an OH, but we've now bound it to this. So this is our backbone, and I'll diagram this all up in a minute here. Oh yeah, and I had 10 CH2s there. Sorry, forgot to mark that earlier. Alright, and it's very interesting to write backwards, I must say. Very different. There we go. So, I have 1 2, 3 fatty acids, and then over here I have a glycerol backbone. Now, why do we call it a glycerol backbone? Well, here's what glycerol looks like. So it's a 3-carbon chain, and on every carbon is an alcohol group. And so guess what we can do? We can take a fatty acid with its carboxyl group, perform a condensation reaction with the alcohol group on a glycerol. We do that 3 times, and we have ourselves a nice energy package here. So this is not going to have the reactive carboxylic acid groups. It's not going to affect the pH of the environment around it. And it packs them in a little more tightly than if we just had fatty acids. So this is, from a spatial perspective, denser storage, and from a protecting the environment inside the cell perspective, we have something that's not going to try to react with things around it. So it's very stable. It's chemically stable. And the name of this one is trilaurin, because it has 3 lauric acid fatty acid chains in it. You don't have to know the naming system or anything like that. It's just an example. So what we do is, when it does come time to burn this for energy, we can perform hydrolysis reactions and we can break these fatty acids off. We get the glycerol back, we get the fatty acids, and then the fatty acids go through the metabolic process and they start getting chopped up into 2 carbon pieces. Or, if there's an unsaturated fatty acid here that we can use for some sort of hormone synthesis, make a steroid out of, we can do that too. So you can break it off and then you can send it, do the work Omni stuff with it, make yourself a steroid. Okay, so this is what a triglyceride looks like. And then in terms of, so these are all oils and fats. So triglycerides are oils and fats. I want to be clear about that. And if you remember, as it gets more saturated, melting point goes up, it stays more solid. And the reason for that is, and I'm just going to draw a very rough example. So if we have a saturated triglyceride versus something with an unsaturated chain in it, we get a big difference in shape. So we've got our backbone, and it's kind of like all 3 just lay straight. Sometimes they show us being a little more rounded. But if we have an unsaturated, we get a bend from the double bond in the carbon chain. So these are our carbon chains. This is our glycerol backbone. So it's a very minimalist approach to drawing these. But what happens is, when it's solid, you've got to stack nicely. You've got to stack together. But if it's unsaturated, it takes up space. It's harder to stack them tightly together, makes it more likely to be a liquid. So the bend makes forming a solid more difficult. Because remember, they got to kind of stack together to be a solid. These are going to more easily, so we're talking about saturated now, stack into a solid structure. These are harder to stack because they're taking up space. All right, that's going to be a problem. It's really hard to do. Actually, I can do that with my own pinky. I just got to hold that one back. These 2 fingers, they're very closely related. They don't like to be too far apart, apparently. There we go. All right. So unsaturated, saturated, and so we can boom, boom, boom. We can stack. If we do this, I can't get as close, and I have the issue here. And if we can't get them as close, they don't interact as strongly. Just harder to keep them that way. And so our melting point here goes up because it stays solid, whereas over here, melting point goes down, so it's like more liquid. and this is more solid. So butter is an example of probably the most commonly used saturated triglyceride. It's very heavy in saturated fats, whereas most oils are unsaturated. So typically oils are like unsaturated because they're liquids at room temperature. Fats are solid at room temperature. I think that's actually the official description between the two. So typically plants use oils, animals have fats, by the way. So, you know, it's bacon fat and olive oil. Now that's not always true. You know, there's coconut oil, which is a solid at room temperature, and so it's pretty saturated, but there's always the exception that proves the rule. Now, why do we worry about trans fats and hydrogenation and all that? Well, butter isn't cheap, not compared to, say, canola oil or something like that. And so you can use a hydrogenation reaction and it will take a unsaturated fatty acid chain, and this could be in a triglyceride, so you don't have to break off the pure you don't have to break off the fatty acid by itself. Like, you can just do this with an oil, so you don't have to separate all the pieces. But I don't want to draw all that, so I'm just going to draw cis fatty acid here. So we go, looking at my notes, drawing on the paper, and it seems to be working. I didn't put anything where it wasn't supposed to be. We have, you know, our cis form here. We have a catalyst plus some H2 gas, thus the hydrogenation part, and we get the trans form. Or whoops. Nope. No double bond. Sorry, I looked at the wrong part. We get a saturated. Now, here's what happens if we have just the catalyst. So if we take this, and it doesn't react with the H2, this is what I'll show next. We get the trans form. Boom, boom. 1, 2, 3, 4. 1, 2, 3. I always just look at the mountain peaks. And then 1, 2, 3. 1, 2, 3. OH, double bond O. That's how you draw these fast. You get the trans form. So what can happen is, you want to make a saturated fat cheaply. You take an oil, you hydrogenate it. That's what happens. So we get basically a cheap butter substitute. If you are making Twinkies for a living, this will increase your profit margin greatly. And substitute. There we go. Plus, it's more shelf stable, typically, than butter. It doesn't have all the other dairy stuff in it. It's just an oil. So, you do this with triglycerides, you get a cheap butter substitute. How could you lose, right? What's the problem? Well, if you don't do it well, you get a bunch of trans fats too. And they didn't used to worry about that. So now they have these like trans fat free hydrogenated oils, like I can't believe it's without butter, and no trans fats. Like those type of things show up. And that's just because they've gotten better at catalyzing these reactions, doing these reactions. By the way, this catalyst, if you're curious to know, it is platinum metal. Platinum is a magic metal, does all sorts of exciting things. So what you do is you take your oil, you put it in a big vat, and then you have a plate of platinum you stick in there, or some sort of, you know, platinum geometry thing, and then you bubble hydrogen gas against that platinum. So maybe you do a flat plate, you bubble underneath, and then the oil will react with the H2 along that surface, and you will get saturated fats. So you'll go from oils to fats. And then you ship that off. You know, you make all of your margarine or Crisco or whatever, and then you just ship it straight off to the Twinkie factory, and they make Twinkies out of it. It's a win-win for everyone. So, you get a bunch of trans fats in there, though, you can start getting the heart plaque for reasons I talked about before. It never hit the levels of let's just fry chips in nothing but trans fats level difficulties, where then, dam bursts, and out goes not water. But yeah, so that's what we can do with these. So that's kind of like what are trans fats, what are saturated, unsaturated. There used to be a lot of discussion about saturated fats creating a higher risk of heart disease, and that was a commonly held truth for a long time. And then recently, the study was kind of looked back on that started it all, and it was just like 30 guys in the 50s, and then it was like, oh yeah, the ones that had more saturated fat had more heart disease. And so there's some question about whether that's actually a big deal or not today. I think it's, at this point, it's just kind of like fat is fat. There are some unsaturated fats that are very important. So this would be an omega 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is an omega 9 fatty acid right here. I just counted the bonds. And so having things like omega 3s and omega 6s, so having the double bond a little farther back, very important for our diet. Probably more important than worrying about whether or not something's a saturated fat is just worrying about you get the right unsaturated fats. That's, I think, where things are today. I don't know, you guys took a nutrition class, you tell me. Or you're going to take a nutrition class, and in which case maybe I helped you or I hurt you on an exam. I look forward to having you find out and then me not, because I'm not the one taking the test. Alright, so that's it for triglycerides. So they're long-term energy storage. You've got 3 fatty acids that are all tied to one backbone together, and we can break them off one at a time and do chemistry with them, do biochemistry with them. So triglycerides are an energy storage medium because they are a fatty acid storage medium, and fatty acids can be broken away, and then they are chopped up to pieces and then used for metabolic energy. But they hold a lot of energy, and we'll bring numbers into play later, in a later section. So they hold a ton of energy, but it's very slow to get to. So this is maybe like, not only is it your savings account, but it's like your offshore savings account in Zurich. And so to get to that money, you have to, go fly there, and then you strap it all on your body and you sneak through the airport and you come back. It's a very slow process, but there's a lot of money in that bank account because you didn't pay any taxes on it or whatever, which is why you have to sneak it back through the airport. So I'm not really worried about any of you doing that, by the way. If you have a lot of money in Zurich, why are you in my class? Or if you are, welcome. Welcome aboard. Have fun trying to smuggle hundreds of thousands of dollars through U.S. Customs all the time. Alright. So, you have your suit in 2 sizes, right? You have like the one you fly there in, you got the one you fly back. You can't have it look all baggy when you get there, and you can't have it look like there are pieces of money all over you when you come back. So there's a lot to think about there. Very difficult. And I guess there's always the Bahamas. It's a nice boat trip. Anyway, that's enough about that. So that's what's going on here. So this is a type of lipid. This is the energy storage type, by the way, triglycerides. And just to be clear, this is a wonderful representation right here. This is amazing. This is just great. But if you really want to get into the details, just be aware that this is what they look like in terms of like a chemical formula. So you just got those 3 levels, each with a fatty acid attached. And this is glycerol, so it can perform 1, 2, 3 condensation reactions to get this thing put together. So we can bring in a fatty acid, 1. We can bring another fatty acid, 2, and we bring another fatty acid and attach it, 3. So 3 waters pop off as well. You guys have seen plenty of condensation reactions. I won't push you through another one. But if you're unsure about it, feel free to draw one up, take a crack at it, and if you have questions, just let me know. Alright, so next we are going to talk about phospholipids. So they make up all of the cell membrane, and they are not used for energy storage. Let me be clear about that. If you are burning through phospholipids for energy, you're in trouble. Very similar to triglycerides. You can think of them like they are a modified triglyceride. But I'll leave it there, so I'll leave it for the next video.